Something is deeply wrong in the deep sea. A creature that should have starved to death years ago is still alive, still moving, and somehow surviving on 0 calories. Why does the giant isopod break the rules every other animal must obey? Why can it endure starvation, crushing pressure, and even being dragged to the surface when almost everything else would explode instantly? And if it is so unkillable, what finally brings a creature like this down? Follow this story because the deeper we go, the stranger it becomes. No one has ever witnessed a giant isopod eat a single piece of food. Not during the day, not at night, and not once in the last 758 days. Yet it remains alive, moving, and somehow functioning on what appears to be no energy at all. For now, it is the only animal on Earth that seems capable of living on 0 calories. These things refuse to die. Most deep-sea animals explode the moment they reach the surface due to extreme pressure changes, but giant isopods pulled from depths of over 2,000 meters survive as if nothing happened. So why are they built with such absurd resilience? Why evolve the ability to withstand a world they never naturally visit, and what could possibly kill something like this? To even begin answering that, we need to understand what they truly are. And strangely enough, they are bugs. Or almost bugs. If you flipped a damp rock in your backyard, you'd find a tiny gray pill bug that curls into a ball when touched. A giant isopod is essentially the same creature genetically speaking. Same phylum, subphylum, class, and order. Just one is 60,000 times heavier and lives in the abyss. But that doesn't explain why giant isopods evolved to be nearly indestructible. Stop feeding a garden pill bug and it dries out and dies in about 2 months. Humans at best last a few weeks without food. The logic is simple: the bigger you are, the more energy you burn. A blue whale needs millions of calories a day just to exist. So how does a giant isopod survive years without eating? Has it somehow broken thermodynamics? Not quite. Up to this point, by all logic, a creature this size should starve to death within months. But life in the deep sea is not logical. It is pitch black, near freezing, and almost empty of food. Nothing grows down there. When you compare this to the world of the pill bug, where food is everywhere, you see why evolution pushed one lineage toward extreme starvation resistance while the other stayed small and well-fed. But saying evolution needed them to survive starvation still doesn't explain how they actually manage it. Even existing burns energy. Humans lying in bed all day still consume thousands of calories just keeping their cells alive. So how does a giant isopod stretch a single meal across years? Because its body runs at the absolute edge of life. Giant isopods are ectotherms, their internal temperature hovering just above freezing. They spend no energy generating heat. Their metabolism is so slow it borders on suspended animation. Every cell performs the bare minimum required to qualify as living. They barely move, conserving energy with a discipline no surface creature could match. They are essentially in a permanent state of deep rest. But a slow metabolism is only half the secret. The other half begins when food finally arrives. In the deep sea, that usually means a massive whale carcass falling from above. When that rare moment happens, the giant isopod does not simply eat until it is full. It gorges until its rigid exoskeleton can no longer lift its swollen body off the seafloor. It becomes a heavy living stone, packed with dense lipid reserves stored in its liver. These biological batteries are so energy-rich that the isopod can sip from them for years. A stranded human might survive longer if they had more body fat. This is the same idea taken to an extreme that only the deep sea could produce. And this isn't hypothetical. We watched this entire strategy unfold in real time through the most famous isopod ever recorded, number 1. He wasn't given that name because he was special. It was simply the first ID tag at Toba Aquarium in Japan, but the title stuck. In 2009, number 1 consumed an entire horse mackerel. He gorged so intensely that every possible energy reserve was filled to its limit. And then, for reasons no one understood at the time, he simply stopped. For the next 5 years, every month, keepers tried to feed him. They offered mackerel, squid, anything he might want. Every time he ignored it. He sniffed it, tapped it with a leg, and walked away. In total, he refused food for more than 800 days. And then in 2014, he died. But the autopsy revealed the shocking truth: he had not starved. His internal reserves were still intact. He was running on the energy of that single meal he'd eaten when Barack Obama was only a year into his first term. Something else, old age stress captivity, finally caught up to him. But hunger did not. And the fact he survived at the surface at all was its own miracle. Remember, number 1 was no longer in the deep. He was living at the surface, a place that should have killed him instantly. For almost any creature from the abyss, being dragged upward is a death sentence. Bring a blobfish to the surface and it collapses into a shapeless mass. Bring up a deep-sea rockfish and its eyes burst outward as its stomach is forced through its mouth. It is gruesome but predictable. Their bodies rely on extreme pressure to maintain structure. Remove that pressure and the internal gases expand violently, just like a shaken soda can exploding the moment it's opened. That is why the legendary giant squid almost never attacks ships. If you ever see one at the surface, it's already dying. The deep sea keeps its animals alive by keeping them compressed. So how does a giant isopod survive being hauled 2,000 meters upward without turning into paste? Because its body is built for a different set of physics. Unlike most fish, giant isopods have no swim bladder. They don't float. They walk the seafloor like armored tanks. Without gas sacs, there is nothing inside them that expands when pressure decreases. No expanding gas means no catastrophic implosion. And then there is the armor. Their exoskeleton is a masterpiece of segmented plating. Each layer overlaps the next, allowing them to curl tightly into a ball and shield their vulnerable underside. This armor is engineered to withstand the crushing weight of 500 meters of water. Yet because it is rigid and not supported by internal gases, it keeps its shape even at sea level. It's as if they are wearing a suit of armor that works equally well at the bottom of the ocean and in the vacuum of space. So giant isopods don't starve, they don't explode, and they don't collapse under pressure. But there is something that can kill them, and ironically, it often comes from themselves. Giant isopods are not brilliant thinkers. Thinking requires energy they cannot spare. They are scavengers driven by instinct. When a large food source appears like an alligator carcass used in experiments, dozens swarm in. They pile on top of each other in a chaotic frenzy. And because their vision is poor, they often bite anything that feels like meat, including each other. Their armor normally prevents real injury, leaving only a confused isopod wondering why the food bit back. But there are predators that truly can kill them. Sharks can tear right through them in a feeding frenzy. Octopuses, far more calculated, can grab an isopod pry apart its armor and pierce the soft interior with a beak designed for cracking shells. Still, these threats don't explain why giant isopods became giants in the first place. Why would an animal in the deep sea grow so large? Wouldn't becoming a giant only make it more noticeable to predators like sharks? Surprisingly, the benefits of size outweigh the risks. While deep-sea sharks will attack them, predators are not common enough to counter the advantages of gigantism. For scavengers, size is power. When a rare whale carcass hits the seafloor, being large lets a giant isopod hold its position and tear off bigger chunks of meat before competitors arrive. And most importantly, the bigger the body, the more food it can store for the years ahead. Imagine knowing that the next meal you eat might have to last half a decade. You would want as much surface area as possible to pack energy into. That is exactly what the giant isopod's body is built for. But there's another advantage. A whale fall might land miles away. For a tiny isopod, walking 5 miles across the seafloor would take weeks, so long that it would burn more calories on the journey than the carcass could ever replace. It would die before it arrived. A giant isopod, on the other hand, crosses the ocean floor in enormous energy-efficient strides. Its size allows it to reach the feast before it disappears into the mouths of other scavengers. Evolution rewarded the lineages that could move faster, eat bigger, and store more. What's strange is that no other isopod lineage on Earth followed this path. Terrestrial isopods barely reach an inch in size. Even Antarctic species that benefit from polar gigantism only grow to about 5 inches. Other large marine isopods like Cerulolus or Glyptonotus reach just around 3 inches. Beyond that, nearly all isopods remain tiny. Only the deep-sea Bathynomus group evolved into true giants, nearly triple the size of the second-largest isopod line. It shouldn't have been possible. Their flattened bodies, simple gill systems, and heavy armor impose natural limits that normally keep isopods small. If giant isopods didn't exist, science would simply assume the isopod design was incompatible with large size. But gigantism came with a terrible cost. Because they wear a suit of armor, they cannot grow gradually. Their shell doesn't stretch. To get bigger, they must molt, shedding their exoskeleton. And for a creature built to avoid wasting energy, molting is a nightmare. It drains enormous energy reserves. And while the armor is off, the isopod becomes soft and defenseless, like a walking buffet item waiting to be eaten. A predator encountering them mid-molt would end them instantly. So they evolved a strategy no other crustacean uses. They molt in halves. First, they shed the back half of the armor and wait for it to harden. Then they shed the front half. At all times, at least half their body remains protected. It looks ridiculous, like an animal wearing only pants or only a shirt, but it keeps them alive through their most vulnerable stage. Yet for all their resilience, one weakness completely destroys the giant isopod's survival strategy. There is one thing giant isopods cannot survive. One danger so simple, so ordinary, that it feels almost unbelievable considering everything else they endure. Warm water. These creatures can withstand crushing pressure, near freezing temperatures years without food, and even survive outside water for over an hour. But a slightly warm bath can kill them almost instantly. When exposed to warm water, their metabolic system unravels. Oxygen demand spikes far beyond what their slow deep-sea physiology can support. Enzymes misfire. Chemical reactions cascade out of control, and within moments, the isopod dies. For an animal adapted to the cold, slow world of the abyss, warmth is a death sentence. It is their kryptonite, the one flaw in a creature that otherwise feels nearly indestructible. Giant isopods remain among the most unique animals on Earth. Their biology is a masterpiece shaped by starvation, darkness, and pressure. They can endure what would instantly kill nearly anything else. But even the most adaptable life form has limits. And for number one, the isopod that survived 800 days without eating it may have never wanted to leave the deep sea to begin with. The surface was never his world. Yet he clung to life far longer than anyone thought possible, powered by one extraordinary meal and a body perfected for the quiet, bitter cold of the ocean floor. Thank you for watching. If you want to explore why worms become terrifying when they leave their natural habitat, you can continue the journey here.